So some molecules have more than one valid Lewis structure. Follows the rules, looks really good. So let's draw Lewis structure for ozone. Ozone is O3. So O3, there's no other way to do it, 3 oxygens in a row. Number of electrons, valence electrons, 3 times 6, 18. So I've got 2 there, 4, 6, 8, 10, 12, 14, 16, 18. I need a double bond because I don't have enough electrons. So this is the atom that needs more. The atom next to it has an octet, and so I'm going to take one of these lone pairs and just move it. So I'm going to move a lone pair to become a bonding pair. Of course, this is not how the compounds, the molecules actually form. This is just how we go about representing them. Do all those atoms have octets now? Yeah, they do. This one, 2, 4, 6, 8. This one's got 2, 4, 6, 8. Oxygen here, 2, 4, 6, 8. We'll do a lot of counting to 8 by 2s. 2, 4, 6, 8. Who do we appreciate? So that's a good Lewis structure. These oxygen atoms, they're all atoms of the same element, but they are individual atoms. So we could think of these as triplets, perhaps, and this is Susie and Patty and Debbie. I don't know, right? 3 different girls. They look the same because they're identical triplets, but they're different people, right? And so if we've got a double bond here between Susie and Patty, I don't remember what their names were, S and P. Look at that, I picked SPD. Where's F? That's weird. Anyway, so S and P here, Susie and Patty, they've got the double bond, and Debbie over here is like, why didn't I get a double bond? Well, why didn't we give Debbie the double bond? Why did we give it to Susie? No good reason. There's no reason. So how about we draw the structure giving the double bond to the other oxygen? Equally valid Lewis structure. Just to make them look exactly the same, we'll put the dots there too. There's 2 different structures. In nature, ozone exists as an average of these 2 molecules. It's not that there's 2 different ones, or that the double bond moves back and forth. There's actually 2, just one, but it's an average of these. Lewis theory doesn't handle this very well. So we can draw 2 different structures. They're called resonance structures. And to indicate that, we put a double-headed arrow between the structures. So those are the resonance structures of ozone. So here we have those 2 resonance structures. The actual structure is more like this. There isn't a double and a single bond. Both of the bonds are exactly the same. And that can happen because the electrons are actually delocalized. They're shared over the whole molecule. Lewis theory doesn't do that. In Lewis theory, the electrons are localized. They are attached to or between specific atoms. So this is the actual structure, but we can't really represent it well. So all we do is we draw all the possible resonance structures and put double-headed arrows between them. So this is a little bit like having a mixed breed dog, right? So German Shepherd, Golden Retriever, they have a puppy, and the puppy might look like this. The puppy does not some days look like a German Shepherd and other days look like a Golden Retriever. It doesn't go back and forth. It doesn't like flash. Like, oh, it's a German Shepherd now and it's a Golden Retriever. It doesn't go back and forth, right? That's ridiculous. This doesn't go back and forth either. I remember being confused about that. Resonance is like, oh, well, it's vibrating back and forth between them. No, it's an average, a hybrid. So this is a hybrid dog. So this would be like, my husband, he's of Japanese descent and I'm of Swedish descent. And so you look at our kids, they don't look really like either one of us, but they sure look like each other. They're a hybrid, a mixture, right? The reason that this happens is that when those electrons are delocalized, that results in a stabilization. It's called a resonance stabilization. It's a lowering of energy. And this idea of resonance stabilization is a big deal in organic chemistry. Write a Lewis structure for the nitrite ion. Include resonance structures. So here we have a nitrogen and two oxygens, and we have to figure out how to put them together. I mean, we could put nitrogen on one end and then the two oxygens, or we could put nitrogen in the middle and the oxygens on the outside. So one of the guidelines is the more electronegative element is probably going to be in a terminal position. Oxygen's more electronegative, and so we're going to go with the one on the bottom. Also, I happen to know that's the right one. Counting up valence electrons. We have two oxygens, each 6, and nitrogen has 5, plus 1 for the negative charge, and so 18. Especially on an exam, use your calculator to do that, or at least to check your mental math, because it's a shame to get something wrong just because you added badly. Okay, so 18 electrons. Well, there's 2, 4, 6, 8, 10, 12, 14, 16, 18. Not enough. I need to make a double bond. I'm going to take a lone pair from the nitrogen because it has an octet, and I'm going to give that as a shared pair over here with this oxygen that doesn't have enough. Now we've got octets for everybody. Put brackets around this and indicate the charge. That's the nitrite ion. But again, here we have these two oxygen atoms, and this one got the double bond and that one didn't. Why? Well, because it just happened to be how I put the electrons around, right? No good reason. I can also draw it with the double bond to the other one. So I can put the double bond over here and the single bond over there. What's different between these is I've just put the double bond in a different position. I'm moving multiple bonds. That's mostly what resonance structures are. It's not rearranging the atoms. It's not drawing a structure with oxygen in the middle and the nitrogen on the outside. That would not be a resonance structure. So these are the two resonance structures for the nitrite ion. Any questions? Formal charges. So I showed you how oxygen likes to form 2 bonds, chlorine likes to form 1 bond, etc. This is a more rigorous way of figuring out which is the best of the Lewis structures that you might possibly be able to draw. So the formal charge is a made-up thing, kind of like oxidation states are made up. They're not actual charges. So this is made-up charges that we assign to each atom, and it's the charge that an atom would have if all the bonding electrons were equally shared between the bonded atoms. And so, and we don't consider electronegativity when we're doing this. If you like math equations, go ahead and use this. The formal charge is equal to the number of valence electrons that that atom has minus the number of bonding electrons and half of the non-bonding and half of the bonding electrons. That works, but I think it's tedious, so I'm going to show you a different way to do it. The rules here, the sum of the formal charges add up to the total charge on the molecular ion. So if it's a -1 ion, all the formal charges will add up to -1 if you're doing it correctly. Small or zero formal charges are better. And if you have to have formal charges, which is always with an ion and sometimes with molecules, you want to put the negative formal charge on the more electronegative atom because it's an electron hog. So give it what it wants. Give it the negative. So formal charge is a way to help us figure out what is the best Lewis structure. Because for some of these, you can draw different ones. And so here we've drawn two different ones for hydrogen cyanide. Here's carbon in the middle or nitrogen in the middle. So I'm going to redraw those down here. So this one has carbon in the middle, a triple bond, and nitrogen with a lone pair. That satisfies the octet rule. And over here we've got hydrogen with nitrogen in the middle, a triple bond, and carbon with a double bond. A lone pair. You can use the number of bonds to tell you which of these is better. That works for a lot of things. It doesn't work for everything. Here we see that carbon has 4 bonds, 1, 2, 3, and the nitrogen has 3 bonds. And that's what carbon and nitrogen like. Over here, the nitrogen has 4 bonds, and the carbon only has 3 bonds. So I can tell just by that this is not the right one. But let's see how we use formal charges. So for the formal charge, I think of this as maybe being a business partnership where hydrogen and carbon and nitrogen each brought some resources to the business and they were doing really great, and then they decided to stop doing business together. And so they're just going to divide stuff up. So what we're going to do is we better get to the correct one. We're just going to cut the bonds in half. And remember that the bond has 2 electrons, and so each of these is going to give 1 electron to each atom. And then we're going to look to see, well, what did hydrogen bring to the business? How many valence electrons? 1. And how many is it leaving with? 1. 1 minus 1 is 0. That has a 0 formal charge. How many valence electrons did carbon bring? 4. And how many is it leaving with? 1, 2, 3, 4. 4 minus 4, 0. How many valence electrons does nitrogen bring? 5. And how many would it leave with? 5. When those elements form the number of bonds that are unpaired electrons in their atom Lewis structures, they end up with 0 formal charges. Let's look at this one over here. Again, we're going to cut the bonds in half. Hydrogen always has a 0 formal charge because it makes 1 bond and it brought 1 electron, and so it's always going to be 0. Here's the nitrogen. Nitrogen brought 5 valence electrons to the business, and it's leaving with 4, right? 1, 2, 3, 4. 5 minus 4 is a positive 1. So the formal charge on the nitrogen there is a positive 1. Carbon brings 4 electrons when it participates in this partnership. And when the carbon is leaving, 1, 2, 3, 4, 5 electrons. 4 minus 5 is a negative 1. It has a negative 1 formal charge. Now, I don't know about you, but I like that better than this business up here. Just cut the bonds in half to see what they leave with, and compare that to the number of valence electrons they had coming in. Sometimes they leave with more, sometimes they leave with less. Ideally, they would go away with the same thing that they brought in. Everybody would break even.
Are instances where they all have 0 formal charges that are more stable?
Yes, that's more desirable for all the formal charges to be 0.
But it's not impossible that it would form like the version on the right? It would stabilize the version on the left or something?
Yeah, this isn't impossible, but it's not likely.
Right.
And if that did form, it would probably react very quickly to form something else. Yeah. This rearranging to form that is not going to happen. It's way too complicated. Really what we're using the formal charges for is we're given a molecule or a polyatomic ion, and we need to write a Lewis structure. And sometimes we can't tell how it's supposed to be connected, and so there's several different possibilities. You draw different possibilities, you look at formal charges. If you come up with one where all the formal charges are 0, that's it right there. There's probably not another one that's all 0.
Is the rule of thumb still to put the most electronegative atom in the center?
The rule is the most electronegative atom is usually on the terminal, on the outside.
Okay.
Yeah. Yes?
So the formal charges throughout the molecule is something other than answers that most likely is not used?
Well, sometimes it's not possible, even with a neutral molecule, it's not possible to draw a Lewis structure where all of the formal charges are 0. When you have a polyatomic ion, somebody is going to have a formal charge. Because here we see that these formal charges add up to 0, because this is a neutral molecule. 0 plus 1 minus 1, that adds up to 0. So let's do some examples. Assign formal charges to each atom. Yeah, each atom in the 3 resonance forms of N2O. N is central. Which resonance form is likely to contribute most to the correct structure of N2O? So this is not what you would necessarily pick to put nitrogen in the middle. Molecules tend to be symmetrical, and so what I want to do is I want to put oxygen in the middle. But oxygen is more electronegative, and they tell us nitrogen's in the middle, so we got to go with that. So we'll put nitrogen in the middle, and oxygen on oxygen on one side and a nitrogen on the other side. Add up the electrons. We've got 2 nitrogens, each 5 electrons, and 6 electrons from the oxygen, so that's 16. So we've got 2, 4, 6, 8, 10, 12, 14, 16. Did a little different that way. I just kind of started going around, and now this nitrogen is really short, and this nitrogen and the oxygen both have octets. Not enough electrons. We need to do more sharing. So let's take this lone pair from the nitrogen that has enough and have it share with the neighbor. It's a little bit like Robin Hood. Steal from the rich and give to the poor. So this nitrogen, by sharing its lone pair, it still has an octet, but this nitrogen is better. It's got 6 now, but it still doesn't have an octet. So let's have this nitrogen share its other lone pair. And now we see that this nitrogen has 2, 4, 6, 8. This nitrogen has 2, 4, 6, 8. The oxygen has 8. Octet rule satisfied. How else could we draw that molecule? Could we give the triple bond to the oxygen? Don't see why not. Nitrogen, single bond, nitrogen, triple bond, oxygen. So the nitrogen in the middle doesn't need any lone pairs. This guy has an octet, and this guy has 1 lone pair. You can count them up, it's the same number of electrons. I just moved them around. There's one more. I have a total of 4 bonds here. I've got a triple bond and a single bond. What if I did 2 double bonds? Would that be the same number of electrons? Yeah. So let's try that one. Ooh, not that fat. Nitrogen, double bond, nitrogen, double bond, oxygen. So I've got 2, 4, 6, 8 electrons, 10, 12, 14, 16. Everybody's got an octet. So these are 3 resonance structures. The atoms are connected in the same order. The hip bone's connected to the thigh bone, But double bonds are different. Triple bonds are in different places. Assign formal charges. So once you get a little bit familiar with this, you can look at these atoms and say, well, here the nitrogen has 3 bonds. I bet that nitrogen has a 0 formal charge. And we could look over here and, ooh, that oxygen has a double bond. I bet that one has 0 formal charge. But let's do it thoroughly. So this first nitrogen always brings 5 electrons, and how many does it leave with? 5, right? 1, 2, 3, 4, 5. 5 minus 5, 0. Okay, the nitrogen in the middle, he brought 5, and he leaves with 1, 2, 3, 4. So that's positive 1. And oxygen over here, oxygen brings 6, and here it's leaving with 7. So that's negative 1. So we've got 0, plus 1, and negative 1. Maybe I'll write those up here so we can see them better. 0, plus 1, and negative 1. Okay, let's do this next one. Cut them in half here. Nitrogen brings 5, because that's how many valence electrons it has. And here it's leaving with how many? 7. So that's negative 2. And the nitrogen in the middle brought 5 and leaves with 4. So that's positive 1. And the oxygen brought 6 and is leaving with 5. So that's plus 1. So we've got minus 2, plus 1, and plus 1. Check that those add up to the overall charge. Overall charge is neutral. Those should add up to 0. If you screw up, it's not going to add up, and that'll alert you that you need to fix something. And this last one. So nitrogen brought 5, and here it's leaving with 2, 4, 6. So that's a negative 1. The nitrogen in the middle brought 5, leaving with 4. It's plus 1. Oxygen brought 6, leaving with 6. That's 0. So how do we choose? Which is the best one? We want the lowest formal charges. None of them have all 0. That would be the best, but it's not possible here. This has the highest. If you just add magnitudes, 2, 1, and 1, that'd be 4. This would be 2, and that would be 2. Just absolute values. So it's not the guy in the middle. Not that one. And so then we look at this one and that one, and how do we choose? If there's a negative formal charge, it's best to put that on the more electronegative element. Which is more electronegative, nitrogen or oxygen? Who's closer to fluorine? Oxygen. So on this one, the negative charge is on oxygen, so this is the winner. Any questions? Cut the bonds in half, compare what the atom brought and what it's leaving with. Draw the Lewis structure, including resonance structures for diazomethane, CH2N2. Carbon is central. For each resonance structure, assign formal charges to all atoms that have formal charges. This one can get messy. So they're telling me that carbon is central. Well, that could mean that all the things are attached to the carbon. That'd be carbon being central, right? Let's see if it works. We've got 2 hydrogens, each with 1 valence electron. We've got 2 nitrogens, each with 5, and we've got a carbon with 4. So I believe that's 18. 2 plus 10 plus 4? No, that's 16, right? Anybody have a calculator? This is 4 and 2 is 6 and 10. 16, okay, there we go. So, I'm not going to do the dots on the bonds anymore. 2, 4, 6, 8, 10, 12, 14, 16. Don't put lone pairs on hydrogen. He's too small, he can't handle it. I ran out of electrons, what do? Make a double bond. Who can I make a double bond with? If I took a lone pair from this nitrogen and did a double bond with carbon, the carbon would have too many electrons. So that's not going to work. And this is the same issue. This isn't going to work. What's wrong is I put the skeleton together wrong. I did it on purpose. So we need to reevaluate our skeleton. So let's just take off those electrons. It said that carbon was central, so we can't just put carbon on the end. But what if we took this hydrogen and put it on a nitrogen? Is carbon still central? Yeah. Let's see if that helps. So I got 2, 4, 6, 8, 10, 12, 14, 16. Well, what can we do here? I could take this lone pair and make it a double bond. And now the nitrogen has 8 and the carbon has 8. The hydrogens are good, but this nitrogen isn't. And again, I can't take this and share it because the carbon would have too many. So moving the hydrogen to the nitrogen seemed to help. So let's try that with the other hydrogen. Yeah, what am I doing? I'm going to get those out of the way. I'm going to put the hydrogen over here, and I just moved the lone pair up there. 2, 4, 6, 8, 10, 12, 14, 16. I didn't lose or gain any electrons. Well, what's wrong here? Nitrogen's got too many, right? This nitrogen has too many, so let's take that lone pair and give it to somebody who doesn't have enough. You give it to the carbon. Just move it next door. So everyone's happy except this nitrogen still. But now there's a lone pair on the carbon, and I can share that with the nitrogen. And now how is it? Nitrogen's got 2, 4, 6, 8. Carbon has 8. Nitrogen 2, 4, 6, 8. So that's good. Let's look at the formal charges right now. How many bonds does nitrogen have here? Well, it's got 1 on this side, and 2 on that side, 3. Right? That's what nitrogen likes. Because nitrogen comes in with 5 valence electrons. If it has 3 bonds and a lone pair, it leaves with 5. Carbon comes in with 4. If it's got 4 bonds, it leaves with half of each of those. It leaves with 4 zero formal charge. That molecule has all 0 formal charges. So that's probably the best one. But it says including resonance structures. Well, we've got these bonds in here, but we saw one earlier where we put a triple on one and a single on the other. And so we can do that here as well. Do hydrogen, nitrogen, we do a triple bond with the carbon, a single bond with the other nitrogen. And we shouldn't play favorites, so we can put the triple bond to the other nitrogen. These are resonance structures. This one in the middle, is that going to have 0 formal charges? Maybe let's start in the middle. The carbon has 4 bonds. Carbon brings in 4 electrons, it would leave with 4 electrons. Because what we're doing is we're imagining cutting these in half. So that carbon is 0. What about this nitrogen over here? He brings in 5, he leaves with 4. This one's plus 1. Over here, he brought 5, he's going to leave with 2, 4, 5, 6. So that's negative 1. And then over here, this is just like the mirror image of that. The nitrogen with the 2 lone pairs is going to be negative 1, and the nitrogen with the triple bond is going to be plus 1. You can't have two zeros? Well, we want zeros. That's the best one. Yeah. And so here what it did, it says assign formal charges to all atoms that have formal charge. So what I did is I didn't write all the zeros. Those are all zeros. It's the one with, if you get all zeros, that's the best. Well, you would still have to do these if it tells you to draw resonance structures. But if they're just saying draw the Lewis structure, you just find the one with the lowest formal charges and you're done.
If it doesn't have the Lewis structure where all zeros, then closest to the highest one.
Yeah, you want to, if you've got to have formal charges, you want to find the one with the lowest formal charges, and then the negative one go on the most electronegative element.